The problem statement from Gate Physics 2017 reads as follows. The minimum number of NAND gates required to construct an OR gate is. This is a multiple choice question with only one correct answer, and we need to find the correct one. So what do we mean by Boolean algebra? So Boolean algebra performs three primary operations. The first is conjunction. Conjunction means the output will be true only when all the inputs are true, and this is often denoted using the dot symbol or the multiply symbol. The disjunction means the output can be true if at least one of the inputs is true, and thus this is denoted by the plus symbol. Negation is whatever the input, it will be inverted. The input is high, the output will be low, and vice versa. So this is often denoted by bar, right? This is the bar symbol. All right. And the values that we use here are zeros and ones. So for instance, 0 times 0, so 0 is a value, so 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, 1 times 1 is 1. Similarly, 1 plus 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 again is 1, 1 plus 1 is 1. And there are two other laws called De Morgan's law. These are often used to convert to conjunction to a disjunction and vice versa. You can see this is converting a multiply to an addition, and with using some negation. So solving the problems, we use these De Morgan's laws. The Boolean algebra is often implemented, the conjunction, disjunction, negation is implemented using something called the logic gates, which we see here. In the top row here, you can see the name of the gate, and these are the algebraic expression. I told you the bar is for negation. You see this dot is there, so this is multiplication or the conjunction. You see this plus, this is the disjunction, or these also called the OR gate, and this is the conjunction, is also called the AND gate. You can see the symbols here. So for instance, NAND is interesting, it's nothing but the AND gate followed by an inverter. That's why you see this circle of the NOT gate here. What is a truth table? In the truth table, you list all the possible combination of inputs and you try to find the output, because we already know the algebraic expression. So for instance, let's talk about the very simple gate, NOT gate. So NOT gate has only one input. The possible combinations are 0 and 1. And this is an inverter, so it will be 0 bar, which is 1, and 1 bar, which is 0. So very simple truth table. AND gate has two inputs, A and B. So the possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And X is nothing but A times B. So we know that 0 times 0 will be 0, 0 times 1 will be 0, 1 times 0 will be 0, and 1 times 1 will be 1. Similarly, you can do for OR gate and any other gate. The interesting thing is that the NAND gate, I told you, is AND followed by a NOT. So if you invert this 0, you'll get 1. Invert this 0, you'll get 1. Invert this 0, you'll get 1. Invert this one, you'll get 0. That's how we get the NAND gates. Key thing to note here is that AND gate cannot be used to perform the three primary operations. Note, I told you conjunction, disjunction, and negation. So these are the three primary functions. So AND cannot do that. AND can easily perform conjunction, but it cannot perform negation. There's no way it can invert a signal, right? Similarly, OR can perform a disjunction but cannot perform a negation. However, there are two gates, NAND and NOR, which can perform all these three functions depending on how the inputs are arranged, right? And hence these are called universal gates. So why they are called universal? Because they can perform the three primary functions on their own using 2, 3. Let's say using 3 NAND gates, you might be able to implement an OR gate or a NAND gate or an AND gate. So similarly, just by using one flavor of logic gates, you can get all the logic gates and all the primary operations. That's why they are called universal, right? So here is a NAND gate. So this is a NAND gate you see on the top left, and we have implemented an inverter. So I'll try to solve this. So we know that the truth table of an NAND gate looks like this. So A bar is the so A and A are the inputs. Note the two inputs are A and A, and let's say the output Y. What is the output? We'll see. So there are only two inputs possible. Either both are 0 or both are 1, because both are the same, and we know that Y equal to A times A whole bar, right? So 0 times 0 bar will be nothing but 1. Similarly, 1 dot 1 bar, which is 1 bar, which is 0. So what's happening? When the input is 0, the output is 1, and when the input is 1, the output is 0. This is nothing but a NOT gate. So when NAND gate is used in this configuration, which you see on the top right, you will get an inverter. So we saw that just by using a NAND gate, we have created an inverter. Similarly, you can create any other gate or any other combination logic for that matter just by using the NAND gates. Similarly, you can create a NOT gate from a NOR gate, and you can see here we have used 3 NOR gates to create an AND gate, 4 NOR gates to create a NAND gate. So you can use any, but all of these are the same flavors. All of them are NOR. That's what we mean by universal gate. So we just saw that there are 2 universal gates, NAND and NOR. So and we also saw that why are they called universal, because we can get any logic just by using, let's say, 2, 3, 4, 5 number of NAND gates we saw in that slide. So here we want to construct an OR gate just by using NAND gates. So it's very simple. So let's first write the algebraic expression for OR gate. So let's assume that the inputs are A and B and the output is Y. So this is very straightforward. So this is A and B are the 2 inputs, and this is the OR gate, and this is the Y output. So I have just written this. Now, but NAND gate requires a multiplication form. This is an addition form. So what I'll do this. I'll write Y can be written as Y bar and then bar. So if you take the negation 2 times, the logic does not change. So I'll simply replace the value of Y here in the inner bracket. So it will be A plus B whole bar and then this. Now I'll apply De Morgan's theorem in the bracket. So we know that according to De Morgan's law, A plus B whole bar is nothing but A bar dot B bar. So I'll write A bar dot B bar whole bar. Now I'll do a change of variables. So let's assume A bar is nothing but C and B bar is nothing but D. So this will become CD whole bar. This is nothing but a NAND gate, right? CD whole bar. This is expression for a NAND gate. So what I have done is that I have obtained that Y, the expression Y, note that Y was A plus B, right? And this is Y, and this is C, and this is T. So we needed Y equal to A plus B. This is also equal to CD whole bar. But C and D were not the inputs that were given to us, right? We were only given 2 inputs, A and B. So what do we do here? We saw that we saw A bar equal to C, right? And we also know how to create a NAND gate using just an inverter. Sorry, how to create an inverter just by using a NAND gate. So how do we do that? We saw that in that slide that if you provide same input, same value to both the inputs, like this. So just look at only this part. So what we'll get? So this output will be what? A bar. You saw that in the slide. So C equal to A bar, we know that. That's what we wanted to implement. Similarly, we know that B bar equal to D. So how do we get the value of D? Similarly, just like we did for the other case, we'll apply both the inputs like this. B. So if you apply both the inputs to this NAND gate are B, the output would be nothing but B bar. So so now the inputs are A, B, and the output is Y. So this is nothing but the OR gate that we have implemented. And now what we need to do is we can simply count the number of NAND gates that are there. This is the first gate, this is the second gate, and this is the third gate. So we require 3 NAND gates, right? So answer should be 3, but the question says minimum. What's that? So can we go below that? No, we cannot go less than 3. There have to be at least 3 gates, but we can go higher. How? So let's say you implement again this logic. So this will be Y bar, and you again implement this logic. This will again be Y, right? So how many gates you are using now? You are using 1, 2, 3, 4, and 5, right? Which you don't require actually. So this is not adding any value to this. That's why the question is minimum number of NAND. So you cannot go below 3. You can go higher. You can go 5, 7. So hence the answer will be D, 3. Thank you for listening.